Hi guys, and welcome back to my channel. In this video I want to talk about odd Lewis structures. So basically you should be familiar with how to draw Lewis structures from AP chemistry, but in this video I want to talk about stuff like radicals, like carbocations, like some weird bonding that you see with boron and aluminum and that group of compounds. So basically, we're just building off the basic understanding of drawing Lewis structures that you should already have. So yeah, so knowledge of drawing Lewis structures is basically a prereq for this video. Let's just get right into it. Okay, so first I want to talk about radicals, right? What exactly are radicals? You might have heard of the term. You might have heard of radicals destroying the ozone layer, stuff like that. Radicals are just compounds with unpaired electrons, right? So what does that mean, and what does that make how does that affect the compound's reactivity, right? Radicals are generally highly reactive. And why is this? Because electrons don't like to be unpaired. They like to be paired. They like to be with a partner, right? One of the electrons is spin up, the other is spin down. They like to be paired together. So radicals want to gain an electron so that the unpaired electron can now become paired, or it wants to lose an electron so that the unpaired electron can just leave, right? So now all the other electrons are still paired. So basically a radical is very reactive because it can either gain or lose an electron and it'll become happier. So it just, there's a ton of reactions that radicals can undergo such that they gain or lose an electron. And either way, it's going to make the compound more happy. So exactly what I wrote here, it wants to gain or lose an electron. And biradicals, that's just, an extension of radicals where you have two unpaired electrons, hence the bi in the biradicals. So here are just some examples of radicals that I've drawn. Our first one is nitrogen monoxide, and the second one is nitrogen dioxide, right? So you can see, you should be able to draw these Lewis structures pretty easily, right? You should be able to count the number of valence electrons. If you count the number of valence electrons, you'll see that nitrogen is 5, oxygen is 6, right? So we have 11 total valence electrons, and then automatically you should know, okay, this is an odd number, which means that we should have a radical, because one of the electrons is not going to be paired. So, and if you count all these, all of our valence electrons in bonding and in lone pairs, you'll see that we have 1, 2, 3, we have 2 in each bond, so we have 7 there, and then 2 lone pairs, which makes it 11. So you can see how I've drawn this, Lewis structure pretty easily. And you can do the exact same thing with NO2, and you should be able to draw these Lewis structures yourself. So that's all I want to talk about radicals for now. In a future video, I'm going to go more in depth onto radical stability and radical reactions. But in this video, I just want to introduce the notion of what is a radical. Now I want to talk about carbocations. And again, I'm just going to brush on what carbocations are. In another video, I'm going to talk more in depth on carbocations and what influences their stability. What is a carbocation? A carbocation is just a carbon atom with only 3 bonds, as opposed to forming 4 bonds like normal. So carbon usually likes to form 4 bonds. That gives it its happy octet and has a formal charge of 0. But with a carbocation, you only have 3 bonds. So now the carbon doesn't have an octet, right? It does not have an octet. This carbon only has 6 electrons, right? Because we have 2 from each bond, so we only have 6 electrons total. So this means we basically have an incomplete octet. So not yet 8 electrons, right? So this makes it very, very reactive. So let's look at some points about carbocations, right? Our carbon is sp2 hybridized with an empty p orbital. And why is it sp2 hybridized? Because we only have 3 sort of electron domains, our 3 bonds, and our fourth, we don't have a 4th electron domain because there's no lone pairs and there's no other bond. So we can draw this, if we want to talk about the geometry, we can talk about this as trigonal planar with a p orbital that's empty. So if we want to sort of draw this a little more with the geometry in mind, we have our R groups, right? I'm just denoting them as R. That just means any sort of group that can come out of, that is bonded to the carbon. So I can draw my R groups, and then my p orbital is going to look like something like this, right? And that p orbital is going to be empty, and it's going to be perpendicular to the plane of to the plane of the molecule. So since carbon only has 6 electrons from our 3 bonds, it is electron deficient, right? Because usually it has 8 electrons. Now it only has 6. It's electron deficient, which means it should have a positive charge, positive formal charge. And this is why we call it a carbocation, right? And in organic chemistry, you'll also hear about the term carbanion, right? And when you see anion, you should think negative charge, right? So with carbanions, we're thinking negative charge. With carbocations, we think positive charge. So that's why, because this is an electron deficient and it has a positive formal charge, that's why this is called a carbocation. And again, these are extremely reactive and they're very high in energy. Why is this? Because the carbon isn't happy. It doesn't have an octet. So this lack of the octet makes it very, very unstable. And so because of this instability that comes with forming a carbocation, you cannot isolate a carbocation. Like I can't have a jar, like a beaker filled with a carbocation, but instead we observe carbocations. We know that they exist because they appear as intermediates in reaction mechanisms. So say we start with some compound where we have 3 different groups and sort of a leaving group. So this is just a little intro to organic chemistry, but I won't talk much about it here. If one of these groups sort of leaves, if our leaving group leaves, like a bromine or something like that, then we end up forming something like a carbocation. And we can observe that we know that this actually forms because through experimentation, we observe these mechanisms, and these mechanisms show that a carbocation is formed and then something else reacts with the carbocation. So I just want to make it clear that you cannot like isolate a carbocation. You can't have a beaker full of a carbocation. It's way too high in energy and it's way too reactive. Okay, so now we're going to get into sort of weird structures that come with the boron and aluminum and the group 13s. And we'll go into 2 different types of bonding as well. With these structures, we'll talk about 3 center 2 electron and 3 center 4 electron. And I'm going to explain all of this on the next 2 slides, so don't worry about this right now. So I just want to introduce in this slide why these certain elements have very weird Lewis structures. Boron and aluminum, when they bond, they actually form incomplete octets, and they're semi-happy with 6 electrons. So it's a little bit weird. They are not as unhappy, as unstable with 6 electrons as something like carbon would be. So they can actually be isolated when they only have 3 bonds, or they only have 6 electrons. And you should have this should have been mentioned in an AP Chem class, but I just wanted to review it. So if we look at boron and aluminum, basically something like BH3, right? This exists, and if we draw the Lewis structure for this, we have BH. We have 3 H's surrounding our boron, right? And you can see that our boron only has 3 bonds and it doesn't have any lone pairs, which means that we only have 6 electrons on the boron, but this can actually be isolated in certain situations. Okay, so what does this mean about, boron and aluminum and, other elements in that group? They form excellent Lewis acids. So why is this, right? Because these boron and aluminum compounds have, only 6 electrons. It still kind of wants an octet, right? Octets are always, very stable. But, with 6 electrons, boron and aluminum are still semi-happy. But because it doesn't have an octet, these can act as really, really good Lewis acids. They can accept electrons. And you'll see that you'll have formation of what we call coordinate covalent bonds, which means that in that bond, both electrons come from one atom. And it's gonna be more clear with this next example. So let's look at this next reaction. We have Bf3 plus Nh3 goes to Nh3 Bf3. So let's draw this out, right? We have our boron compound, our boron fluoride compound, and if I draw this out, it'll look something like this with our empty p orbital. Remember that because we only have 3 electron domains and no lone pairs. So this is sp2 hybridized, and that means we have an empty p orbital. Next, right, we have our NH3, which looks something like this, right? Trigonal pyramidal. So now our boron Bf3 is really, really Lewis acidic. Why? Because first of all, we have our empty p orbital, right? Empty p orbital. And we have our incomplete. These are sort of the same ways, saying the same thing twice, but I just want to make it clear. Incomplete octet. And second, we have fluorines connected to the boron, right? And what are fluorines? Fluorines are super electronegative. They're very, very inductive. It's going to draw electron density away from the boron. So we already have really, really low electron density on the boron, but now we have electron density again being drawn away, which means that our boron is going to be super, super electron poor, and so it's going to be very willing to accept electrons. Okay, so this electron pair on the nitrogen is just going to attack this boron and form a bond, right? Because we have this empty p orbital and our boron is very electron poor. We have an electron rich site on our nitrogen. So this is going to act as our Lewis base, and our boron is going to act, our Bf3 is going to act as our Lewis acid. So we have this sort of attacking going on, and this is the same sort of attacking you'll see with nucleophile, electrophile reactions in organic chemistry. So you should be familiar with this, a little bit of this concept of electron poor sites being attacked by electron rich sites, because electron poor sites really want electrons. Electron rich sites want to sort of get rid of their electrons. So we have this attacking that happens, and we form our Lewis acid base adduct. And if I draw that, it'll look something like this, with our boron connected and our 3 fluorines. And our boron now has a negative formal charge, and our nitrogen has a positive formal charge. So this is our final adduct, which is what we call this a Lewis acid base adduct. So our ammonia donates 2 electrons to form a bond with boron. And you can see that this is a coordinate covalent bond, right? Both of our electrons in that bond are coming from the nitrogen. You can see both of those electrons in the nitrogen are being donated to boron to form that bond. And that's why we call it the coordinate covalent bond. And here's just one more example. We have Bf3 plus fluoride ion goes to form Bf4 minus. This is exactly, a very similar example. We have our Bf3 with our empty p orbital and very electron poor boron. Then we have our fluoride ion. And so we have a very high, electron dense site on the fluoride ion. We have an electron poor site with our boron. So we have this attacking mechanism that happens. And then we form our Bf4. Bf4. And this has a negative charge, right? So hopefully this sort of made sense with Lewis acid base adducts and why stuff with incomplete octets are going to be very, very good Lewis acids, because they want to accept electrons to get an octet, right? Okay. Now I just want to talk about 3-center 2-electron bonding, and this is this is sort of like a weird bonding thing that you'll see a little bit mentioned on USNCO exams and stuff like that, and it's something you should be familiar with. I tried to gather everything, all the useful examples of 3-center 2-electron bonding, and on the next slide 3-center 4-electron bonding. But obviously there are other examples I have not, I haven't been able to compile. But hopefully this gives you an idea of what this bonding sort of is, and you can be able to apply it to other situations. Okay, so if we look at something, I've just given a bunch of examples here. If we look at dimerization and polymerization, right? These are 2 key examples that have this 3-center 2-electron bonding. And it only usually happens with our weird elements, with our borons, with our aluminums, with our berylliums, right? These are sort of the weird elements that have kind of funky bonding in general. So let's just look at these examples. So first we have AlCH3, 3. So CH3 is also just methyl, a methyl group, so I've abbreviated these to just methyls. But you can see that, aluminum has 3 bonds, it has our 6 electrons, and that looks like a normal sort of Lewis structure, right? But when we polymerize this, right, this dimerizes to Al2CH3, 6. Okay, so this is weird, right? How do we draw this structure? And you can see I've drawn it here. And I just want to explain where the 3 center 2 electron bonding comes in. So we see that these carbons have 5 bonds. That doesn't make any sense, right? Carbon cannot have 5 bonds. It can only have a max of 4 bonds. It only has, it doesn't have any d orbitals to hybridize. So it can only have 4 bonds in total. So how can it have 5 bonds in a situation like this? And this is where we have weird bonding that happens. This isn't these aren't normal bonds here, right? I'm going to draw them with a different color actually. So these aren't normal bonds. These are 3 center 2 electron bonds. And let's explain what normal bonding is. Normal bonding is when we have 2 atoms, right? Let's look at hydrogen. 2 atoms is H2, and we share 2 electrons, right? Share, because in each bond we just have 2 electrons. So normal bonding is called 2 center. We have 2 atoms, 2 atoms, 2 electron bonding. So that should make sense, right? We have 2 atoms and we're sharing 2 electrons. That's 2 center 2 electrons. Now we're having 3 center 2 electron bonds. So that clearly is different, right? It's not normal bonding, and that's why we're allowed to have 5 bonds with the carbon. So let me explain exactly what's happening here. With these 2 bonds, right, our top 2, we're actually having, this bond is sort of like a 3 center bond. We have aluminum, carbon, and aluminum again, sort of all sharing electrons. And they're all sharing 2 electrons total. This is a little bit weird to wrap your head around, right? But this allows the carbon, because the carbon is only sharing 2 electrons between both of these quote-unquote bonds, it technically only has 4 bonds, right? Because this combination of both of these bonds is just 2 electrons, which is just one normal bond. So hopefully that makes a little bit of sense, right? It's not violating the octet rule. So these aluminum carbon bonds, so this is also called like something like a bridge bond. Sometimes you might see it called a bridge bond. And you can see that there's just one long bond that 3 atoms are interacting in this one long bond, sharing 2 electrons. And that same thing is happening on the bottom, where we have 3 atoms interacting, sharing 2 electrons. So this is definitely a difficult concept, and it was hard for me, and it's still confusing for me. But hopefully this made it make a little more sense, and we'll look at another, 2 more examples that are very, very similar. So it'll make hopefully make more sense with these extra examples. So again, we look at BH3 and B2H6, right? Our next example. You can see BH3 is again just a normal Lewis structure. Now we look at B2H6, and you can see these middle bonds are again the same exact situation. You might say, okay, this is a hydrogen, right? How can hydrogen be bonded to 2 things, right? Hydrogen can only have 1 bond, right? That's how it normally is denoted with Lewis structures. But in this case, we have 2 bonds connected to a hydrogen. That doesn't make any sense. So how can this happen? This can happen because we have 3 center 2 electron bonds here. So this BHB thing is just one entire sort of bond. This is just one big bond where we have 2 electrons being shared across all of these 3 atoms, and that's why we can have technically 2 quote-unquote bonds connected to our hydrogen, because that's just 2 electrons in total. And that's totally fine. That's the equivalent of one normal bond. And again, the top is the exact same thing. We have a 3-center 2-electron bond here. Next, there's just one last example. It's very, very similar to the BH3 versus B2H6. Here we have BeH2. So here we can see normal Lewis structure. And this is polymeric BeH2, but here I've just drawn Be2H4. So if n equals 2, but you can draw this, multiple times for n equals 3, 4, 5, etc., right? But here we have BeH2, 2. So you can see that in these bridge bonds, again, you always want to look for the bridge bonds because this is where you see the 3-center 2-electron bonds. We have hydrogen being connected to 2 different atoms. That doesn't make sense. But then you realize, okay, this is 3-center 2-electron. So that's okay because our 2 bonds are basically just one bond, right? Just think of this entire bridge. Just think of our BeH-Be as just one big bond, right? I wrote this before, but I'm just trying to emphasize the fact that this is not really 2 bonds. It's just these 3 atoms all sharing 2 electrons together, rather than like normal, we just have 2 atoms sharing 2 electrons. So hopefully that makes sense. Last example I want to show is Trihydrogen Cation, which is very important in interstellar matter chemistry. So, in between stars in the interstellar matter, there's this ion actually pops up a lot. And this is the H3 plus ion. So you automatically know, right? Hydrogens, each hydrogen has 1 valence electron. We have 3 hydrogens that has 3 valence electrons, but then we have a positive charge, so there must only be 2 valence electrons. And we only have 2 valence electrons available for bonding, but we have 3 atoms. So again, 3 atoms, 2 electrons, 3 center, 2 electron bonds. So we have these hydrogens sort of arranged in a triangle, all bonding together. So everything is just bonding together. We think of this as just one big bond, right? One big bond where we have 3 different atoms sharing 2 electrons. So hopefully that made a little bit of sense. And the one I would definitely remember is BH3 and B2H6. This comes up a lot on the USNCO. So if you have to remember something, remember that one. But I think once you really understand what a 3-center 2-electron bond is, you can pretty easily draw all these Lewis structures. It's just difficult to wrap your head around at the first time. And another fact you should know is that B2H6, this dimer of BH3, is the major form. So it's the major form of borane. So if I had borane in a jar, it sort of spontaneously dimerizes and forms these 3-center 2-electron bonds. So lastly, I want to talk about 3-center 4-electron bonding. And this is a little bit different than 3-center 2-electron bonding, which we just talked about. But in this case, I'll show a few examples and it'll make more sense. So let's look at the first example. We have AlCl3 and Al2Cl6. So this is a dimerization example. So we draw AlCl3, just our normal Lewis structure. And here, next to this, I've drawn Al2Cl6. And I want to notice something that's important, right? You can see that we sort of have these AlCl3 subunits. You can see that there's 2 subunits, right? And then I've drawn these arrows, right? And you can see these arrows are basically coordinate covalent bonds. And that's why I mentioned this previously, right? That's why I wanted to, make this term familiar before I got to this section, because these are just coordinate covalent bonds. The chlorine, an electron pair, a lone pair on the chlorine, is just being donated to form a bond with the aluminum. And that creates, right, so we have these Al3Cl3 subunits. One chlorine from one subunit is going to attack the lone pair from that chlorine is going to attack an aluminum on the other subunit. And we have, a chlorine from the other subunit attacking the aluminum from the first subunit. And these arrows denote these coordinate covalent bonds. And now we want to see, where does 3 center 4 electron come in, right? Why do we call it 3 center 4 electron? There must be 3 centers or 3 atoms, and there must be 4 electrons being shared between those 3 atoms. So let's again look at the bridging bonds, right? We want to look at the bridges. So we look here. That's our top bridge and our bottom bridge, just as we did with, with our 3 center 2 electrons. And you can see that with our first bond, our normal AlCl, our aluminum chlorine bond, that's 2 electrons. There's 2 electrons in that bond. In the next bond, we had a coordinate covalent bond forming, so we had 2 electrons from the chlorine being donated to form that bond. So we also have 2 electrons in this bond. So we basically have 3 centers. We have our aluminum chlorine and our aluminum again, right? These 3 centers. And we have 4 electrons being shared between the 3 centers. We have 2 electrons in one, 2 electrons in the other, 4 total, right? And this exact same thing happens on the bottom, where we have 3 centers and 4 electrons. So you can see that this is basically just 2 subunits and coordinate covalent bonds forming such that these subunits are joined and a dimerization occurs. So just a trivia fact is that AlCl3 forms a dimer in the gas phase. So it dimerizes in the gas phase, but after heating it further, right, after warming it up, increasing the temperature, the dimer breaks down into AlCl3. And that makes sense, right? Because as temperature increases, entropy starts to play a bigger role rather than enthalpy. And thus we're gonna have it favoring the monomer phase, the AlCl3 phase, because that creates 2 of them, which means that there's higher entropy in our system. So the next thing, so now I just want to show one more example, and this is with beryllium. So beryllium chloride. If we look at BeCl2, we just get, our normal Lewis structure, similar to how we drew BeH2, but this time it's BeCl2. And here I've drawn BeCl2, 2, so where n equals 2. So if we look at this, right, you can see that we have our BeCl2 subunits. You can see these subunits pretty clearly. And then we have these coordinate covalent bonds with the chlorines, right? Chlorine is attacking the beryllium. The other chlorine is attacking the other beryllium. And we have these coordinate covalent bonds being formed, right? And this creates our 3 center 4 electron bonding, right? So basically the dimerization 3 center 4 electron bonds are just coordinate covalent bonds forming between monomers. So we can see that. I'm just gonna circle it. You can see that these arrows are just coordinate covalent bonds. Okay. And you can see that, right, there's 2 electrons from the coordinate covalent bond, there's 2 electrons from the normal bond, so there's 3 centers and 4 electrons. The next example is hypervalent bonding, and this is a really important example, and I actually saw this in a question on USNCO, and that's how I learned about it to begin with it. That's how I first actually started to learn about it. So this is especially useful, this idea of 3 center 4 electron bonds is especially useful for trigonal pyramidal electron geometries. So let's look at this example where we have SF4. This is a trigonal pyramidal electron geometry, trigonal pyramidal. So what we would think with the Vesper theory is that our sulfur is sp3 dehybridized. Right? We would think this. And we would also think that the axial bonds, right? If we ask the question, right? This is the question I want to ask. Are axial or equatorial bonds in SF4 longer, and why? So our intuition would tell us, okay, there's an electron pair here on the equatorial position. This electron pair is going to repel these axial bonds greater than it's going to repel these equatorial bonds, right? Because the axial bonds are closer. They're closer, if we just look at the image, we have our electron pair. These axial bonds are closer than our far away equatorial bonds. So what does that mean, right? There's a closer proximity. The axial bonds are closer in proximity to the lone pair. That means there's going to be greater repulsion because the bonds are just electrons, right? They're just essentially electrons in bonds. So this lone pair is going to repel the electrons in the bonds. That's going to make the axial bonds longer because we have this repulsion that happens, and to minimize the repulsion, it's going to go farther away. So we would think axial bonds longer because higher repulsion, right? So this is half correct. The axial bonds are longer. The axial SF bonds are longer, but this is not really the correct reasoning. So what exactly is the correct reasoning? The hybridization of our sulfur is not sp3d. This is wrong, not sp3d. What is the hybridization of our sulfur? It's actually sp2 hybridized. Okay, so this is a little bit weird. This goes against VSEPR theory. So our sulfur is sp2 hybridized, and we can sort of see this, right? We can see this trigonal planar sort of idea, geometry happening here. We see that this looks trigonal planar here with our equatorial fluorines, our sulfur, and our lone pair. And then we have these axial fluorines that are just up and down. What's actually happening is this is sp2 hybridized, our sulfur. And remember, if we have sp2 hybridized, that means we have an extra p orbital. So this green thing that I've drawn here, we have an unhybridized p orbital. Okay, so this is really important. Our sulfur is sp2 hybridized, not sp3d hybridized, right? So this is wrong. And because it's sp2 hybridized, we have an unhybridized p orbital. Okay, so what does this mean, right? The p orbital actually forms 3 center 4 electron bonds with our axial fluorines. So if we thought of this as sp3d, right, we would just say that all the bonds are normal, right? All the bonds are 2 center 2 electrons. But because we have an unhybridized p orbital, what is actually happening is we have 3 center 4 electron bonding. So what does that mean? That means these two axial fluorines are bonding, right? They're bonding to the same orbital on sulfur. So this fluorine, this bottom fluorine, is overlapping with the p orbital. The top fluorine is also overlapping with the same p orbital. And entirely there's 4 electrons being shared in total because we have 2 electrons from this bond, 2 electrons from that bond, but they're sharing the same orbital. So basically, our SF axial, right? We're looking at SF axial. The bonds share the same orbital, right? They share the same p orbital because the sulfur is not sp3d hybridized, but it's instead sp2 hybridized, and the only thing left, the only orbital left that's allowed to bond is our p orbital, our unhybridized p orbital, because the sp2 hybridized orbitals are already bonding with the equatorial fluorines, and a lone pair is in one of those orbitals. So we only have a p orbital left to bond. So our axial fluorines are both bonding to the same p orbital. And what does that mean? That means our axial bonds are going to be longer. Why? Because our bonds are going to be less strong. Our axial bonds less strong because they're sharing the same orbital, right? Just think about if you're sharing the same orbital, each bond is going to be less strong because usually we only have 1 orbital per bond, right? So if I have to share 2 bonds with 1 orbital, it's going to be a weaker bond. We're basically splitting that sharing power in half, right? So that's why our axial bonds are longer and not because of repulsions of lone pairs. So that's sort of an important example to keep in mind, and that did pop up in a USNCO exam question. Okay, so now I want to talk about one last example with 3 center 4 electron bonds, and that's it. So the last example I want to talk about is the SN2 pentavalent transition state. This is exactly the same idea as hypervalent bonding. So when we have an SN2 reaction, I'm not going to get into too much of the organic chemistry, but basically you have a carbon. You have a bunch of groups attached to the carbon. Just going to denote them with R groups. And we have some leaving group, right? And in an SN2 reaction, we have a nucleophile that has a lone pair. and the nucleophile is going to attack this carbon, and the leaving group is going to leave, all in the same step. So what does this mean? Basically, we're in an SN2 reaction, we're forming a bond, and we're breaking a bond in the same step, right? We have the formation of a bond and the breaking of the bond in the same step. So our transition state is going to have a bond forming and a bond breaking, because this all happens in the same step. So the highest energy, our transition state is the highest energy part in our energy diagram. So the transition state is going to be where we have a partially formed bond with our nucleophile and a partially broken bond with our leaving group. And so our transition state looks like what I've drawn here. We have our 3 R groups, right? That was just standard with the carbon. And we have our leaving group on a dashed, I've drawn a dashed line, right? This dashed line indicates, what does that indicate? A partial bond. Partial bond. Because this bond is being in the act of being broken. And here again, with the nucleophile, I have the same partial bond, same dashed line, because the nucleophile, the bond is in the act of being formed, right? So none of these are full bonds, they're just partial bonds. So let's look at how the bonding occurs with this carbon, right? This is the exact same idea as what we just talked about. We have these 3 sp2 hybridized, 3 sp2 hybridized orbitals. And remember, with carbon, we cannot have sp3d hybridization, right? So explaining this sp3, this transition state with sp3d hybridization would just be plain wrong, right? Because carbon does not have a d orbital to access. But with it doesn't have a low energy d orbital. So, right, we need to think about this in terms of only s and p orbitals. And that's where this idea of the recenter for electron bonding comes in. We have our sp2 orbitals, and we have one empty p orbital. Remember that if we have sp2 hybridization, that means we have an unhybridized p orbital. And this unhybridized p orbital is what I'm drawing is bonding to the leaving group and the nucleophile. And just like with our sulfur and fluorine bonds, right, we have this p orbital partaking in a 3 center for electron bond. We have 4 electrons. We have the 2 from the bond with nucleophile and 2 from bond with leaving group, right? And we have the 3 centers. We have the nucleophile, leaving group, and carbon, right? And that's where we get our 3 center for electron bonding. And you can see that basically there's one p orbital. And this is also why these bonds, the bonds to the leaving group and the bonds to the nucleophile are long, right? They're not the same. They're not really one bond. It's not as strong as a normal bond. Because we only have one p orbital that's bonding to both, you're sort of sharing that bonding power between the leaving group and the nucleophile. So both of the bonds are going to be smaller, right? Both of the carbon to the leaving group distance is going to be larger. Sorry, not smaller, larger. The carbon to the leaving group distance is going to be big. The carbon to the nucleophile distance is going to be big, because we only have one p orbital from the carbon interacting with both of these, or bonding to both the leaving group and the nucleophile. Okay, so hopefully this video made sense. This was a lot of, lots of weird bonding, and it's definitely difficult to wrap your head around at first. I definitely found this to be one of the most challenging topics to learn. But hopefully this sort of cleared a little bit of things up for you. And yeah, thank you guys so much for watching, and I'll see you guys in the next one.